I'm going to go through a lot of these concepts of probability topics and how they relate to contingency tables. So contingency tables aren't really going to show up until 3.4, but it's going to be the majority of the problems on the homework because these are the problems that I feel are really most important for a realistic situation. So when we have a contingency table, here's an example. We have multiple variables. Specifically, we're focusing in on two variables that are collected from individuals. So this is an exit poll. These are people who have just voted in the election. We've asked them what is their vote and what is their political tendency, either conservative, liberal, some said moderate, and some said none. So it is a hypothetical situation, but it's going to be very helpful to go through these concepts. So we don't exactly have a probability experiment like drawing a card or rolling a die or flipping a coin. Our probability experiment is more like selecting a voter from this group at random. And that's a way to think of it as a theoretical probability. So the number of ways that we can select someone who leans conservative is really just the number of conservatives in the sample, and then the number of outcomes is just the sample size. So a lot of people will really just call this empirical probability. That's where we're getting these numbers, is just our observations, but you can kind of, with just some careful wording, really think of it as theoretical. So just to kind of review, if I word things as what percent of sample voters fall into each category, that would be empirical. If I word things as what's the probability of selecting a voter who is in this category, then it's more theoretical. Later, when we get to binomial probability distributions in chapter 4, really we'll be looking mostly at theoretical situations, and we'll be able to calculate those probabilities using a formula. So we won't even need to observe outcomes to get a good feel for how these different outcomes relate in a probabilistic standpoint. So that's just those first couple concepts of theoretical and empirical probability. Here, our sample space is all of our voters. Our events are different characteristics. So selecting voters who fall into categories like voting for Jessen or leaning towards the conservative. And so you could have a bunch of different events just grouping up based on those variables. And usually an event will be a value of a variable in a contingency table model. So now we're going down, we're going to take a look at some of these notations and probabilities. So we start, before we even get into the unions and intersections, just a regular probability statement, P of A, probability of selecting a voter who voted for Jessen, or probability, a percent of voters who voted for Jessen. Either of these different ideas of empirical versus theoretical probability will give you the same result. We have 34 people who voted for Jessen out of 60 total. We have 23 people who leaned conservative out of 60 total. Each of these can be divided, 34 divided by 60 to get a percent, and so on down. So the third one here is B with that apostrophe. That's the best way to type it out in a spreadsheet, although you can use this bar or this kind of superscript of a C. That's called the complement, and it's when you are looking outside or opposite of an outcome. So a good one to look at is B. We have the probability of selecting someone who's not a conservative, or we could just say what percent of people were not conservatives. And so that's everyone except these 23. That's going to be these 37 if I add up 22, 11, and 4. So that would be not conservative. And in the homework, you might have some problems that get a little deeper into that complementary probability, and I will do a separate video for those. The next one is the intersection, A and B. It's people who meet both requirements, so it's actually where these two things intersect or cross. That's 21 voters in the intersection out of 60, 35%. Or is the union, so the union of A or B is going to be these 34 voters who voted for Jessen plus another 2. So you can see the total for 34 plus 2. We don't want to add the 34 and 23 because that would double count these 21. In fact, that's really what the addition rule is all about. So if you're looking ahead a little bit, in 3.3, we talk about the addition rule. We want to really avoid using the addition rule whenever possible, especially when we have a contingency table. So it's a lot easier to find the union, just basically saying who's in this group or this group. We've got 34 plus 2. If we use the addition rule, we say we have 34 out of 60 in group A. We have 23 out of 60 in group B. And then we double counted the 21, and so that gets subtracted back out. 34 plus 23 minus 21 out of 60 is 60%, or 3/5, and that should be the same thing we get right here. So you really don't need the addition rule. Really the same goes for the multiplication rule. If we continue on here and find our conditional probability, we can take a look at that. So conditional probability is an out of probability. Out of B. So I read this as A out of B. It's really the probability of A given B. So given that we select a conservative, we're only looking at these 23 people. 21 out of those 23 are going to be votes for Jessen. So a really high percent of conservatives voted for Jessen, much more than the overall vote. So 57% of everyone voted for Jessen, 91% of conservatives voted for Jessen. We can really see that good turnout we have for that candidate. And then flipping that around, we're saying out of A, or given that someone voted for Jessen, given they were in this column, what's the likelihood of them being a conservative B? So probability of B given A is 21 out of 34. That's 62%. And again, comparing, 38% of everyone, or of voters, were conservatives. 62% of the votes for Jessen were conservatives. So just comparing that P of B to B given A, or P of A to A given B, since we have a difference there, these are going to be dependent events. And now dialing back here to the multiplication rule, that one says that to find the AND probability, multiply P of B times A given B, or P of A times B given A. I think I chose this first one as an example. So P of A is 34 out of 60 times P of B given A is 21 out of 34. If we look in Desmos, we can see how these 34s would cancel, and it would just be 21 out of 60, and 21 out of 60 is our intersection. So it doesn't really make a lot of sense to use the multiplication rule in this setting, because we can easily count 21 in the intersection or 36 in the union to get these and or probabilities. We're really only going to use the addition and multiplication rule when we don't have a contingency table. And that's rarely going to happen for this addition rule. We can use the multiplication rule, but usually we'll reserve it for problems with sequential events, like selecting two voters and wanting to account for the vote of the first one. So again, that's something that I do with a separate video later in the homework for that problem. Now the last question here, I already talked about dependence and independence. The last question talks about mutually exclusive. Another term is disjoint events. Now all of these, if you look, have the potential to have something in the intersection. You know, each of these is possible. But right here, we don't have a single voter who voted for Banihani with no political tendency. So those two events, if I were to find one as none and a vote for Banihani, that would be mutually exclusive. And so you can kind of see that I typed that out there.